So let's talk about Planck's constant. What is Planck's constant? Well, Planck's constant is a number that comes out of measurements of the blackbody radiation spectrum. So the blackbody radiation spectrum indicates that if you've got light with a certain frequency, that the energy that's carried by that light can only be carried in discrete multiples of h times f, where this h is Planck's constant. And again, we measure that from experiment. From the blackbody radiation spectrum, we fit the data to the experimental or to the theoretical curve that Planck gave us, and then we get this number h. It's called Planck's constant, and it's given by 6.626 times 10 to the minus 34 joule seconds. So that when I multiply by a frequency, which is 1 over seconds, then I'll get an energy, joules. So the way that we can understand Planck's constant is the ratio of photon energy, that quantum, that discrete amount of energy that you can carry with a certain frequency f, to the frequency. So it's energy divided by frequency. And we got to get the same value for every single frequency. So this is the number that we get from blackbody radiation spectrum data. All right, but that's not the only place that it shows up. It also shows up in the photoelectric effect. The photoelectric effect tells us that the maximum kinetic energy is given by some number times the frequency of light that you're shining on that metal surface, minus a constant that depends only on the surface. Now, according to Einstein, this HF is the photon energy. That's the way that it was explained to us, and he won the Nobel Prize for that explanation. So H needs to have the same value when taken from photoelectric effect data and when taken from blackbody radiation spectrum data. And you know what? When we do the experiments, it works. It gives you exactly the same value. All right, so let's go ahead and just do some problems. These are fairly simple. We're just basically going to plug some numbers in a formula. So how much energy is carried by a single photon with frequency 2 times 10 to the 12 hertz? Well, geez. Energy equals HF 6.626 times 10 to the minus 34, 2 times 10 to the 12. Now, as with everything, when you've got scientific notation, what you want to do is the numbers first and then the tens. So 2 times 6.626. Well, that's going to give us 13.2, and then it'll be times 10 to the what? Well, 12 minus 34 is negative 22. What's the unit? Well, geez, it's an energy. Everything was in SI units, so it's in SI units. So that's the answer, 13.252 times 10 to the minus 22 joules. All right, let's do another one. How much energy is carried by a single photon? And this time, I'm not giving you the frequency, giving you the wavelength. So we got to get the frequency in order to use E equal HF. Well, E equal HF, but frequency and wavelength are related by frequency times wavelength equal the speed of light. So that means frequency is the speed of light divided by the wavelength. And now it's just easy. So it's 6.626, 10 to the minus 34. And then it's C is 3 times 10 to the 8 divided by, what was my wavelength? Well, it was 500 nanometers. But I'm supposed to work in SI units. So it's 500. Nano is 10 to the minus 9. So we're going to say 5 times 10 to the minus 7. All right. Numbers first, 6.626 times 3 over 5. And now we got the tens. 10 to the minus 34 plus 8 plus 7. He's negative, but he's downstairs. All right. So then when we go through this, we'll end up with 3.9756 times 10 to the minus 21 joules. And that's the way it works. Planck's constant.